Our third speaker is Misha Kazhdan from Johns Hopkins University. And the talk will be about Phong-Rodrigues Extrinsic vector field processing.
Thank you. Thank you very much. So I shouldn't actually be giving this talk. My student should, but as you've heard about visa issues before, same story, so he's stuck in the US. This talk is about vector field processing. And vector field processing, as you've seen today and yesterday, has numerous applications in geometry processing, frame field design, diffeomorphisms, fluid simulations. I think if you look at the problem that they need to solve, there's traditionally there's two key questions that need to be answered. One is, how do you represent vector fields? You discretize them, you want to find the basis with respect to which you describe a vector field. And the other thing that you often need to do is you need to measure some notion of a smoothness of a vector field. You want to be able to measure its derivative. And these are two challenges that need to be addressed. And the simplest thing you could do is you could say, well, we have a triangle mesh. At every triangle you have a normal describing the perpendicular. So what we're going to look at is vector fields as functions that assign 3D vectors that happen to be perpendicular to the normal within each triangle. And this is great in the sense that this notion of being tangent to the surface is consistent with the geometric normals, but the problem is that the geometric normals are themselves bad. They change discontinuously across edges. And that means if you try and compute derivatives of vector fields in this naive formulation, you're going to have trouble. There's this abrupt shift, unless you force them to be zero or something like that. And so this problem has been looked at in a number of different ways, and even what I'm going to enumerate now is certainly not exhaustive, but there's the discrete differential geometry approach, which really couples the question of discretization and differentiation. It defines a notion of the differencing or Laplacian matrix with respect to a particular choice without specifically defining evaluatable functions. There's a finite elements approach, which define functions that can be evaluated anywhere. And here you deal with the discontinuity problem either by restricting your functions to be continuous to some extent, either midpoint continuous or tangentially continuous, or alternatively, you mess around a little bit with the notion of the curvature of the geometry, typically by looking at the connection defining parallel transport. There's a totally different approach that thinks of vector fields as operators that act on functions as derivations, and there's work in there as well. What we're going to do is we're going to go back 50 years to the domain of rendering, where this problem was recognized. If you have a triangle mesh, and you're trying to, say, ray trace it, you shoot a ray from your camera, it hits the surface, you reflect it through the normal, and you compute the dot product with the light. And the problem is that if your normal is constant across the triangle, you will get piecewise constant rendering, which is not desirable. And the way that this was solved is to say, well, let's define new normals. We'll assign normals to the vertices. We will interpolate them across the triangle. And when we do our lighting calculation, we'll do it not with respect to the geometric normals, but with respect to these interpolated normals, these Phong normals. And that's really what we're going to do. We're going to assign normals to the surface through this Phong model, where somehow it's the Phong model that's really describing the curvature of the surface, that the linearity of the triangle mesh is only in some sense an approximate representation of what we care about. To this end, we'll need maybe one tool, which is called the Rodrigues rotation. And it works very simply. You have two vectors that are non-antipodal, unit vectors, and you'd like to find the minimal angle rotation between them. What do? Well, the two vectors generally will define a plane. The plane has a cross product. You want to rotate about the cross product, and you want to rotate by the angle between the two vectors. Not very complicated. And what's nice is, although this looks like this has some sort of trigonometric expression, it's actually a very simple polynomial quotient of polynomial expression that in fact generalizes to arbitrary dimensions. A very simple equation. Okay. So now we're going to look at the two questions. One is, how do you compute the derivative of a vector field? Or how do we compute the derivative of a vector field? And then how do we represent them? How do we discretize them? And so again, we'll go back to what's standardly done in differential geometry. So in the standard formulation, what do you have? You have some parameterization domain, omega, and you have a mapping from that 2D parameterization domain into 3D, an embedding, which we'll call phi. Okay? And if you have this, what you can do is you can take the differential. It tells you how, if you change along the coordinates of your parameterization, what are the corresponding tangential directions on the surface. Great. With that, you have the tangential directions, you can take their cross products, you have a well-defined notion of normal. And in particular, this allows you to define a covariant derivative. So if you have a vector field and we'll think of it as a function from the parameterization domain into R3, where at every point in R3 it's perpendicular to the normal. What do? You take its derivative, as you would any function, and you just look at the component in the tangential direction. You throw out the normal component. Nothing very fancy there. Okay. Now our setup is a little bit different. We don't have this nice, smooth embedding of parameterization domain into R3. We have our parameterization domain, first of all, is a triangle, and we have a linear mapping of that triangle into R3, but we're given something else. We're given the normals at the vertices. Okay? And those are sort of describing the way we want to think of the surface as curving. So what do? We can define the per position normal through Phong interpolation. Right? And so now we have normals assigned to the surface that are different than the geometric normals. Now we could take the differential of this linear mapping, as we did before, and we'll get tangential directions, but the problem is that those tangential directions will be perpendicular to the triangle's normal, not to the desired normal. Okay, so these are not tangent vectors. So what do? We have our vector n, we have the assigned vector n of p, and we want the tangent frame to be perpendicular to n of p, not to n, so we'll just use the minimal angle rotation. Nothing more, just apply the Rodrigues rotation. Now we have what we'll call the pseudo-differential. It's the differential with this Rodrigues rotation thrown in. And we get the same equation for computing the covariant derivative. Okay? That's it. Now the second question, how do we define vector fields? And how do we discretize the space of vector fields? And here we're just going to borrow very strongly from earlier work. The idea there was you assign a tangent vector to each vertex, and then you extend it or diffuse it in some way into the incident triangles. Now that approach was intrinsic. We're going to use just an extrinsic version of this, where formally what you do is you have the vertex, you have the tangent vector at the vertex, you parallel transport into the incident triangles, and you modulate by a linear function. So let's take a look at how this works in our context. Again, we have a triangle. We have the normals at the vertices. We have the Phong interpolation of the normals into the interior of the triangle. And what do we have? What is the problem that we're trying to solve? We're given some vertex v, we're given a tangent vector shown in blue, and we'd like to transport it along the line segment to the point P inside the triangle. We want to know what is that transported vector. Now, if you look at this, it sort of looks like a Euclidean picture, and you just want to translate the vector, and that's wrong, because it's not a Euclidean picture, right? We have these normals across the surface that are moving. So what do? Well, it turns out you can look at this curve on a different surface. If it has the same normals at every point, the parallel transport is identical. In particular, what we can do is look at this image of this curve, this line segment, on the Gauss sphere through Phong interpolation. Now, there, at every point on the curve, it has the right tangent. It has the right normal. It matches the prescribed normal. So we can look at parallel transport on the sphere, which we know how to do. And what's particularly nice about this picture, if you notice, is that the image of a straight line segment on the sphere under the Phong interpolation is always a great arc. And since it's always a great arc, you don't actually have to integrate over the curve. You can just apply, again, the Rodrigues rotation. Okay. Now that's for a single triangle. What happens if we have a triangle and it's one ring? So there you can see it in blue. Again, we have normals assigned to the vertices. They're interpolated through Phong interpolation into the interior of the triangles. And the normals, I will stress, are continuous. Right? Phong interpolation gives you continuous normals. Now you can do parallel transport into the incident triangles. And by construction, the normals are continuous across, the parallel transported vectors are continuous across all edges emanating from the vertex, from that center vertex. They're not continuous across the boundary of the one ring, but they are continuous because the normals are continuous across there. And so what do? We do exactly what was done in earlier work. We modulate with the hat function. Right? So we now get something that's supported in a one ring, definitionally continuous. Okay? And what's involved in all this? We have three functions. One is Phong interpolation, one is Rodrigues rotation, and one is linear modulation. Right? And our vector field is defined as the composition and the product of these, which means what? It means that if we want to differentiate the vector field, It's just a matter of applying product rules and chain rules to functions that are polynomial equations. Actually, the worst culprit here is really Phong interpolation. You need a square root, so you need to differentiate the square root function. But that's it. Okay. And so really that's really all there is, right? So you have the ability to represent, you have the ability to differentiate. What does that mean you can do? It means you can describe vector fields. You can evaluate them anywhere on the mesh. You can say, what is the tangent direction? It's always going to be perpendicular to the prescribed normal. You can also ask, what is the derivative at almost every point? Across edges, it's not continuous, but it will be continuous within the triangle. Okay? So what does that enable us to do? So for example, we can measure the derivative at every point, the covariant derivative. We can ask what is its magnitude, and we can integrate that over the surface or sum it up using quadrature to get a measure of the connection, the smoothness of the vector field, and that also allows us to do vector field, power field design. We can evaluate the vector fields of power fields in the interior of triangles because these are essentially linear functions. We can even find singularities, more details in the work. More than that, at every point we can evaluate the covariant derivative, and the covariant derivative, as was shown in earlier work, decomposes into different components. Components describing the divergence of the vector field, components describing the curl, and components describing the complement, the anti-homomorphicity. What does that mean? It means if we measure the energy in those individual components, we can compute the associated energies like the Hodge energy or the killing energy, and we can talk about finding killing vector fields. And finally, the ability to evaluate these vector fields and their derivatives pointwise means we can also compute the Lie bracket, or sorry, not compute. We can evaluate pointwise the Lie bracket. At every point, we can evaluate the two vector fields. We can evaluate the covariant derivatives. We can get the Lie bracket. That itself is not a vector field in our space, but you can do a projection onto, least squares projection onto the space of vector fields spanned by our basis. So that's the approach. What are the limitations? There are limitations. So the first thing to note is that our approach is fundamentally a finite elements approach. It is not a discrete differential geometry approach, which means structure preservation is not built in. And so, for example, we said you can define a Hodge energy, and indeed you can, right? But what do we know about the Hodge energy? For the Hodge energy, we know that its kernel, if you look at its spectrum, if you look at the spectrum of the Hodge-Laplacian, the kernel will have a dimension that's twice the genus of the surface. If you look at the two smallest eigenvalues, they are not zero. They're small. The spectral gap is large, certainly, but it's not zero. We're not guaranteeing that we're going to do this. What's another property? Well, so what we have is we start off with our differential of our linear function phi, and then we computed this thing I call pseudo-differential, although I don't think it's called that in the paper, where we just apply the Rodrigues rotation. So this thing over here, this d phi tilde, is not the differential of any embedding function. So properties in differential geometry that use the fact that second derivatives commute aren't going to hold when you use it. So for example, if you want to compute the second fundamental form, traditionally the second fundamental form is symmetric. It's not going to be symmetric. If you want to compute the connection coefficients, if you compute them from an embedding, again, because second derivatives commute, it should be symmetric in the lower indices. It's not, which means the connection we're using is fundamentally not a metric connection. Okay, so where does this leave us in terms of where we want to go in the future? I'm going to leave just 2 points. Certainly, I think there's a lot more, but we won't delve on that. One is we define our pseudo-differential to realize the normals that we prescribe, the Phong normals. And we do this by applying a Rodrigues rotation. Now, this is nice in the sense that what? In the sense that since it's a rotation, the notion of size doesn't change. And that has a very immediate implication that the first fundamental form, or the Riemannian metric defined by the flat embedding, is identical to the one defined by this embedding, because we're not changing the notion of size when we're modifying this differential. It's not clear that that's desirable. If you think of the true surface as some sort of curved surface over a flat domain, maybe the angle is something you want to consider. Maybe you want a scale factor in there that accounts for it. Certainly something to consider. And obviously the question of how do we assign the normals in the first place, that's a degree of freedom. In the earlier work in intrinsic approaches that use connections, you can sort of modify the connection. You can do things with respect to different connections. I think this gives you a similar handle. You can get to modify the connection, the implicit connection, by changing how you assign the normals. That's it. Thank you. Happy to take questions.
Thank you. Do we have any questions? Yes.
Oh, interesting. This thing? Okay. So you mentioned it's not structure preserving, and you mentioned there's a degree of freedom in the choice of normals over the triangle. Phong normals are, I would say, infamously non-integrable. Does this play any role? Is this the reason why it's not structure preserving? And if you chose a set of normals over the triangles that are at least integrable, even if they're not continuous across edges, would that help? Sorry.
I don't have a good answer. I don't know. I would guess the problem is harder, but I don't have a good answer. What I do know, what I can say, is that the fact that it's Phong normals means the image of a line segment is a great arc. And that certainly is important in defining, sort of realizing parallel transport as a simple rotation across a perpendicular. You'd be giving that up and you'd have to explicitly integrate across some curve on the sphere, and perhaps that's doable. I mean, that is doable to some approximation, but I don't know. I don't know. What I would say, sort of, this is not answering your question, but an answering a question that I want to answer, is, so I talked about two handles, right? One is how you define the pseudo-differential, the other one is about the normals. You're talking about the normals. I think there's a more fundamental problem. I think that because we're using Rodrigues rotation, our first fundamental form is identical to that defined by the linear embedding, which means that curvature is 0 on the triangles. No matter what we do, the Gaussian curvature is going to be 0, and it's going to be concentrated discontinuously as a delta function across the boundary. So if you want to get rid of that, you need to do more than normals. So it's not exactly your question, but I think you really have to push on the right-hand side to get better results.
So if I take a triangular mesh and some kind of per vertex normals, and then I consider a continuous surface where at these vertices, its continuous normal is exactly these per vertex normals that you have, then how does your computation differ from the connection of this smooth surface? Let's say with the pullback metric of the Euclidean space.
I think very clearly you can have a big triangle and the surface is undulating, and if you just sample out the vertices, the Phong interpolation is not going to match the true normals at all. Right? So I think if you could, so it's another interesting question is what if you can define, related to Mark's question, what if you can define a normal field in a triangle that is sub-vertex accurate, where it oscillates more? You'd need to be able to differentiate that function as well. But assuming that it's differentiable, maybe it's represented as some sort of texture atlas, you might be able to get more bang for your buck. Yeah, it's certainly the case that one of the things you could see, for example, is if you compute the d phi, if you wanted to correspond to a surface, it would need to be integrable. Right? If you look at the sort of the derivative of each, the x component, the y component, the z component, they would need to be differentiable, or at least curl-free, and they're not. You can show that if they are, this moment that they do, you start having nice properties, but naively, they're not going to have it.
Well, okay, sorry. I think the thing that I was more hoping to see is that, let's say, imagine I have this like simplex structure, and then you take some per vertex normals, you do the Phong interpolation onto all of its edges, and then now imagine for some reason I happen to have a surface that has exactly these normals, right? I still think that there's going to be some still going to be something off, because it seems like your first fundamental form is actually going to be wrong, right? Yeah, because you assume some kind of flatness, whereas...
Absolutely.
Yeah, okay.
Yeah. So you mentioned earlier singularity detection. I wonder, because you're using Rodrigues rotations across the edges, if I understand correctly, also, does the position of a singularity, or can you resolve the position of the singularity, and does it depend very predictably on the values of the field at the vertices?
So the answer is yes, you can, and I would point you to section 6 of the paper, where we do this. You can't do it analytically, but you can do it by search, by repeated bisection search. So we talk about how to do it. Again, the assumption is that if there is a singularity, there's a single one within the triangle, which we're assuming because in some sense, the Rodrigues parallel transport makes like a constant vector field, and then you're modulating by a linear function. So in some sense, the vector field is linear, so it should have just a single singularity, but that's very hand-wavy. And we certainly didn't prove and point out that there might, in fact, be multiple singularities, but assuming that there's one, you can find it.
Thank you.
Last question.
Thank you very much for the presentation. I was just like, I don't know if it would make much sense because you end up with tangent vectors that are not tangent to the actual surface anymore. But since you have now an alternative notion of connection and covariant derivative, did you try to consider the associated geodesics with this notion of
We have not. We've sort of, there's a lot we're going to do. So we're certainly, there's a lot of things we want to look at. We want to look at the torsion of the connection. We want to start really pushing on this. I didn't want to go into the details, but yeah, that's certainly an interesting question to look at. That sort of opens up a lot of different computational directions to move forward on. I think this is really just the tip of what you can do.
Thank you.
All right. Thank you again.